Hi, everybody. Today is Wednesday, April 12th, and we are in ES 2110 statics. And so I wanted to take a look at our schedule and see where we are. We've just finished up our Easter holiday. And so we'll check where we would be in an ideal world and then recognize that the world may not be ideal and it's still just fine. So everybody is still good, whether you are at 100% or not at 100%. All right, so if we take a look at our schedule, in a perfect world, once again, we would be done with chapter 8, which deals with friction. And we would be today taking quiz number 2, which covers chapters 6, 7, and 8. And then we'll start on chapter 5. So unless anybody has any questions so far, I will because of course I can't answer anything about the quiz because not everybody's taken it yet. So if you have any questions about chapter 6, 7, and 8, I would be happy to entertain them. But if not, I would proceed with chapter 5. So anybody have any questions to get started? Okay. All right. So I always have to give a minute because I tend to talk all the time and not let anybody get a word in edgewise. So I hope that was enough time. So anyway, in chapter 5, we start this is a chapter that we skipped. And the reason we skipped is just because, once again, in a perfect world, everybody in this class would have completed Calculus 1. But since that's not always the case, some of you are in Calculus 1. Chapter 5, toward the end, is mathematically very similar to chapter 9. So we'll cover these two as our last 2 chapters in statics. And this involves a little bit more integral calculus later on. Now, today, we're going to just start talking about some shapes and something called a composite shape. And so we'll talk about the fact that an integral sign for some function can be approximated as a summation of something about that function. Okay, so we'll work with this to begin with. But so we're not going to do any integration today, but the work that we have leads up to integration. And so that's the reason that we put 5 and 7 or 5 and 9 together, excuse me. All right, so what we're talking about in chapter 5, in the beginning, we are talking about a concept called the center of gravity, which is tied into an idea of a centroid. And these two ideas, this one is based on mass, more or less, and this one is based on geometry. Okay, now additionally, we're only going to be talking about 2-dimensional shapes when we do this. 3-dimensional shapes also have centroids and centers of gravity, but for our discussion, we're going to be talking about 2 dimensions. Or another way to think about this is we could think about a shape on the XY plane, or we could think about a shape that also has a Z component, but that has a consistent thickness throughout. Okay, so in other words, if this Z dimension is 1 inch, it remains 1 inch and 1 inch all the way through, right? But our discussion will look pretty much the same, but we're going to talk a little bit about what this idea is. The most important thing to remember is that a center of gravity, which is based on mass, and a centroid, which is based on geometry, make some assumptions. But in essence, the center of gravity is a balance point. So what that means is, if you have, for example, I guess we can't see this. I'm gonna get up here. If we have an old-fashioned teeter-totter on a playground, okay, and we have two children of equal mass or equal weight, one on each side of the teeter-totter, if the mass of child 1 equals the mass of child 2, this teeter-totter will be perfectly balanced right here in the middle. If, on the other hand, child number 1 weighs more than child number 2, kind of drum a little bit bigger, mass 1 is greater than mass 2, what's going to happen is this will no longer be a balance point, but that the weight will slant down toward this child, or the balance point will slant down toward this child. Now, there's a couple of different ways that we can reorient that balance point. One would be to slide the teeter-totter over so that this larger child is closer to the balance point than the lighter child. Or if the teeter-totter is fixed, we could also take the heavier child and just have him scoot in more toward the middle in order to balance out. And how we would find that exact point would be kind of a trial and error thing, okay? But this is the idea of a center of gravity. Now, a centroid, which is geometric, the centroid and the center of gravity will correspond if and only if the density and the thickness of the object are homogeneous throughout. Meaning, if we have some sort of a blob, this is in 2 dimensions, right? And we can think about, if we were talking about what the center of mass was, let's talk about something with good symmetry, a rectangle. If this, so for, as far as the centroid, the geometric center of this would be found by bisecting, by drawing a line parallel to both of these and drawing a line parallel to both of these, and where they intersect, or in the dead middle, would be where the centroid would be. In other words, very simply put, if you had this object and you picked it up on one finger and you did not want it to tip, you would put your finger right at that point, and that would keep it balanced. Now, with something that has an irregular shape, it's a little bit harder, but basically what we do is we take the little areas, the differentials of area, and we multiply it by some distance. I'm just going to put R, okay, to the center. And we sum all of those up. So the summation of those individual RDAs is going to be, if we divide it by the total area, which is just the summation of areas, we're going to get some sort of an R, which is the moment arm that would lead us to the center. Now we're going to get some better math than this, but I'm just giving you that idea. So in other words, what that means for us is, if you have something larger out here, it's going to count more toward moving the center of mass toward it, just like the heavier child did, than the stuff that's closer to the middle. Now, if this weight is evenly distributed, for example, if this was a piece of plastic and the thickness was always the same. So in this dimension, I'm not very good at this, but if we had some sort of a thickness ascribed to this object, and that thickness was everywhere the same, so it's an inch thick or whatever, then the centroid and the center of mass or the center of gravity are going to correspond. I guess I should bring up that term as well. Center of gravity is actually based on weight. Center of mass is based on mass. But as long as we're not changing our gravitational field, as long as we're remaining on Earth, the center of gravity and the center of mass are going to be identical to each other. But it could be different if you had a different gravitational field on one side than on the other side. So it's kind of a fine point, but they could be a little bit different. Right. It would still be the same. That's right. As long as the whole thing is subjected to whatever the gravitation is, as long as there's no gravitational anomalies where it's different on one side of the object than the other. Absolutely. So for our discussion, because we're really going to focus more on the idea of a centroid, in general, the centroid, which is usually just called C, generally corresponds to the center of mass, which generally corresponds to the center of gravity. Okay. And in engineering terminology, when we're working on this stuff, we sometimes use those terms interchangeably. Although what we're really going to be finding in the first part of this class, in the first part of this section, and possibly it depends on how much time we have and how far we go into it, we're actually finding the centroid in all the cases, because we're going to be working with areas. If we were working with mass, we'd be working with RDM terms. If we were working with center of gravity, we'd be working with RDW terms, but it's the same kind of an idea. All right, so the way that your authors build this argument is that for any object, the weight is equal to the integral of all of the differential elements' weights. And that x bar, which is the x component of I'm trying to think of the right word for that. Let's just say x component of the distance from the composite object, or from some coordinate to the center of gravity, okay, is equal to the integral of xi dw divided by the overall weight, which could be thought of as being the integral of dw. Okay. And I'm kind of, yeah, I did. I wanted to make sure I didn't do that. And similarly, the y bar, or the y component of the distance from some coordinate to the center of gravity or the centroid, is going to be yi dw over w. Okay. And then not last but not least, but if density and thickness are constant, oops, ran out of paper here. We know that weight, well, we don't even have to know this yet. This comes later. Weight is going to be equal to density times volume, and volume is going to equal area times thickness. So if density and thickness are consistent, what we can see is that this would be rho AT, and this would be rho A, rho B, right? Okay, rho, yeah, let me think about that. Rho A T, and this would be rho AT. So basically, if this is constant and this is constant, they come out and rho cancels and T cancels, and we're just left with y bar is equal to the integral of yi dA over, when we cancel those two out, we just have A. And similar for x bar. Okay. So this is the basic assumption that we use, or this is the conditions that we work with. It's not an assumption that you can generally make, but we can make it here because everything is structured that way. What that means is, therefore, if an object or a shape has constant density and thickness, then x bar, which is the x coordinate of the centroid, is just equal to xida over the total area, and y bar is equal to the integral of yida over a. Right, now we're going to get out of integral calculus for a little bit by saying that for discrete areas, so in other words, triangles, rectangles, shapes under curves that we can identify, a summation of yiai is going to approximately equal to, or maybe be exactly equal to, yida, and the summation of ai is going to equal the integral of dA, which is equal to a. And so in this case, we then can say, if we're looking for x bar and y bar, I've just used y bar here, we can say y bar is equal to the summation of yiai divided by a, and x bar is equal to the summation of xiai over a. So in other words, if we have a composite shape or something that we can identify by different discrete areas, we can add them together in this way, sort of a harmonic average, or a weighted average, I guess is a better way to put it. Which I just thought about that. That's a terrible pun, because we are talking about weight, but we're talking about not weight in the sense of mass times acceleration, mass times gravity, but we're talking about how much, how the distance from the centroid, the farther an object, the farther a space is from the centroid, the more emphasis the equation shows of that weight. Heavy kid on the heavy kid on the teeter-totter once again. Okay, so what does this mean for us? Well, when you take a look at your textbook, the first thing is that there's a page like this, and I apologize, I've removed mine from the book, so I don't know what page it is, but it's somewhere in your book. It's probably on the inside front cover or the inside back cover. But basically, it shows you where the coordinates x bar and y bar are of different discrete shapes. The other thing, there are two other points that I want to make. Sometimes we don't have everything. We'll talk about what that means. But every time we have an x bar and a y bar, we are always talking about a coordinate, which means we have to use the same origin point, whatever that happens to be. So if we look at this circle, for example, and we see that x bar is 4r over 3, let's start with something easier. I'm going to start with a rectangle. I'll just draw a rectangle, because here's the other piece that we want to talk about. When you have something with awesome symmetry, if you can draw a line of symmetry on that shape, the centroid is going to be somewhere on this line. So if you have something that has two lines of symmetry, wherever those two lines cross is where the centroid is going to be. So that's pretty cool. But the thing to remember is that if I want to find x bar and y bar here, I have to reference it from some point. So in other words, I could reference it from here. I could call this my 0, 0 point, or I could call this my 0, 0 point. But in any case, I have to use the same point. And this becomes really important when we do composite shapes, which I'll do before we leave today. But like if you have, for example, this would be a composite shape. a triangle on top of a rectangle. Okay, the centroid of this is here, and my drawing shows me right here that for a triangle, my y bar is h over 3. So that means that my y bar is going to be somewhere here, where if this is h, this is going to be h over 3. Okay, now what I'm getting at is if you reference it from this point as your 0, 0, let's call this height rectangle. Okay, the height of the rectangle, the yi for the rectangle is going to be h sub r over 2, right? Because it's from 0, 0. However, the centroid, the y component of the centroid for the triangle, I can see that it's h over 3, but it doesn't reference from this point. That references from this point. So in other words, I have to recognize that y of my triangle is going to be h sub r plus h, let's say h sub t to make sure we know we're talking about the triangle. It's going to be h sub r, so I have to move from here to here, plus h sub t over 3. That's what I mean by you just have to reference it from a coordinate. Okay. All right, and that will become apparent why later on. But if you have symmetry, you don't really need a formula page. And then later on, we'll get into equations. There's the first part of our work together. We're just going to talk about shapes, either shapes that have some symmetry or shapes that have a lot of symmetry. So for example, here, we talk about quarter circle. We're talking about that. There's a line of symmetry right up here. That really doesn't tell us anything for an X or Y coordinate, but it does tell us that the centroid is going to be on that line of symmetry. For a half circle or semicircle, we have a line of symmetry here, which doesn't tell us much about the Y coordinate, right? The Y symmetry or the Y bar value. However, if we reference from here, symmetry tells us that the X bar is going to be right on that line. So if we call this our 0, X bar is going to be 0. If we call this our 0, that means that X bar would be the radius of the circle. Okay, so just driving that point home. That tends to be a place that people get confused, especially if you have a composite shape like this. Just make sure if you have a composite shape that you're referencing everything from the same 0.
So what's the centroid for both of them?
Yes, that's great. Let's find out. Is that great? Yes, let's find out. All right. So to do this, for example, I'm going to give some dimensions to it. All right. Let's call, let's say h sub r. Let's say that our rectangle is 5 inches tall. And let's say that our triangle is 6 inches tall. And then let's say that this whole, the bottom of the triangle and the bottom of the rectangle is 8 inches wide. Okay. So the first thing is, if I think about this for my X coordinate, my X bar, it's going to be, if this triangle is equilateral, which it doesn't really, I'll draw it a little bit better. If it's like that, if it has a line of symmetry about right here, that means my X bar is just going to be 0 to halfway through this rectangle, which is 4 inches, right? But my Y bar becomes the kicker. So how do we find the Y bar? And the best way to do this is, or the most organized way to do this, is to set up a little table with the components. And this is shown in your textbook on page 242, where you draw out the components and then you fill in the blanks. Okay, so I'll show you what I mean by that. All right, so for our triangle, let's see if I can get everything on the same page here. All right, so there we go. So basically we would draw a little table where we would say the component name. And we have two components. We have a triangle and we have a rectangle. Okay. The next header is the area, and we have X bar and Y bar. Okay. We have the area, which for the triangle is 1/2 times the base times the height. And since they're in inches, I can just put inches squared up here, so I don't have to keep writing inches squared over and over again. So I have 48 divided by 2, which is 24 square inches. The rectangle is 8 by 5, which is 40 square inches. Okay, now the next thing we have, I'm going to just do Y bar because X bar, I'll do one with X bar, but I'm just going to do Y bar just for the sake of interest. The first thing is it's going to be in inches. And the second thing is, like we talked about, I have to decide where I'm measuring from. So I'm going to measure from 0, 0 here in the lower left-hand coordinate. So my Y bar for the well, let's do the rectangle first. Y bar for the triangle. If this is 5 inches, that means that this is 5 inches divided by 2 based on symmetry, or 2.5 inches. Already put inches, I don't have to keep writing that. For the triangle, it's going to be 1/3 of the way up here. So that's going to be 6 divided by 3, or 2 inches above the top of the rectangle. So if this rectangle is 5 inches tall, that means that my Y bar of the triangle is 5 inches plus 2, which is 7 inches. Okay, now I do the pieces, Y bar A, YI, AI, which is just multiplying this number by this number. Okay. And I have my calculator in my office died. I got one right here, but it just takes me a little longer because I have to use my phone. So I feel silly, but there you go. So this is 168. Since I'm multiplying square inches by inches, this is inches to the 3rd. And here I have 40 times 2.5, which I think is 100. It is, good. All right. Also in inches to the 3rd. Okay, now after I get done with this one, I have this column. I add these two numbers together to get the summation of YI, So I add 168 to 100, which is 268 inches to the 3rd. Okay, and then from my work before, I know that Y bar is going to be the summation of YI over the area of the whole thing. So the area of the whole thing is equal to the areas added together, 24 plus 40, which is 64 inches squared. So my Y bar is 268 inches to the 3rd over 64 inches squared. And that gives me a value of 4.1875 inches. Okay, so I'm ignoring the fact that this has a lot of significant digits. We would want to call it maybe 4.2 inches. Okay, but what does that tell you? Well, that tells you this is 2.5 inches, right? And this is 5 inches altogether. So this is going to be somewhere up here, which kind of makes sense, because if you think about the triangle as having, the rectangle as having the larger area, what that's saying is it's just taking the centroid of the rectangle and drawing it up toward the triangle. So in other words, the triangle is weighting it a little bit northward, so to speak, not really north, but upward. So does that make sense? Yay. All right. So if you set up a little table like this each and every time, excuse me, your work will come together really, really well. Now there's something here, there's a couple of things I want to point out. This is a very complicated shape, and they show you how they have broken it down. They break it down into a rectangle and a triangle and a half circle. And you notice they say that equals this plus this plus this, but there's a circle cut out from it. So they subtract off the circle. So what that means is when you have a negative area, it literally becomes a negative area. Okay. The other thing is if they choose this, so there's two things that can be negative. The area itself can be negative if it's cut away or removed from the composite shape. And X bar or Y bar could be negative if they're below the axis. So if you choose this as being your 0 point for finding your Y bars, for example, the Y bar of the rectangle is going to be positive. The Y bar of the circle is also going to be positive. The Y bar of the semicircle is going to be positive, but the Y bar of this triangle, because it's below the 0 point, is going to be a negative. So that's another reason why I really like this problem. So if you look at, here we have a positive area of the rectangle, positive area of the triangle, positive area of the semicircle, and a negative area of the circle. Then X bars are all positive because they're all to the right of that point. But Y bar of the rectangle is positive, but Y bar of the triangle below is negative, and then we have positive and positive. So when you multiply these, you pay attention to the signs. This one would be positive. This one should not be positive. Yeah, this is, I'm sorry, here's my Y bar. This is positive, but this is negative because it's a positive times a negative. This is a positive, and this is a negative because it's below the axis. Now, oddly enough, if you have a negative, it's not odd, but it's really true. If you have a negative area below the axis, it's a negative times a negative, and it becomes positive. So the math works exactly the same way as it does in every other aspect of our lives. But it's a little weird because you think, I cut out something below and it turned into a positive. What it does is it means it's scooting it upward. If it's below, you know, it's scooting it in the opposite direction. So, all right. Now, the only other thing that I would like to tell you is that this term, which is the summation of YI, okay, or could be called the summation of Y bar A, or could be the integral of YDA. This is called the first moment of area. And because it's a moment, we need to reference what it is, where you're taking that moment about. And because you're going upward, you're moving from an x-axis. So it's in of x is really what I guess I would say. And the symbol that we use for that is Q sub x. So Q sub x equals these things. And it's called the first moment of area of x, or in the x. I would prefer in the x. I don't even like that. The first moment of area. I'm just gonna leave it at that. Okay. The other way, Q sub y would be the summation of XIAI, which is the summation of X bar A, which is the integral of XDA, which is also called the first moment. It's just that this has a sub x. So in other words, the variable in here is the opposite of the subscripted variable because you're taking it about this axis or in an axis in this direction. All right. So at this point, do you have any questions? All right, well, there will be a couple of practice problems. Let me see what I've got on our Moodle page and see if we can work one of these. That would be your homework problem. Come down here to chapter 5. There we go. So yeah, 5.1, 5.6, and 5.7. I like 5.7, so I'll write this out and I'll do this problem for you. Okay, so let's come back over here. Oh, you probably didn't even see that. Okay, so for those, Sterling and anybody who's watching this as a recording, all I did was shared a screen from our Moodle page. So
Okay.
let's come back over here and we get back to this. I don't think it ever came off of that view for anyone else. But so we're going to look at problem 5.7 in the textbook. I'm working from the 12th edition. So my problem 5.7 looks like this. So I would interpret that as being a rectangle with a half circle cut out or a semicircle cut out. There's other ways you can do it, which is I had a student one time when I first started teaching this class many years ago, who broke something like this up into about, I think it was 9 shapes. Yeah, it was silly. So don't do it. I mean, give yourself a minute, make it as easy on yourself as possible. So first of all, here on 5.7, we have X and Y. We have a rectangle. The circle is not at the top of the rectangle. The semicircle, I mean, kind of down here. We're told that the radius of that semicircle is 15 inches. And we're told that from the top of the rectangle to the center of the rectangle, excuse me, the center of the semicircle is 20 inches. And that from the center of the circle down is 30 inches. So the total height of that rectangle is 50 inches. Also, since the radius is 15 inches, we can surmise that this would be 20 minus 15 or 5 inches down. We don't necessarily need to know that, but I'm just making that point. We also know that the rectangle is 30 inches wide. All right. So going back to our little table, we start by identifying our components. And then we will find the area of each component. Since these are in inches, we'll do this in inches squared. We'll then find Y bar of each of those components in inches, X bar also in inches. Then we're going to find what we're going to do a summation where we say Y times YI, which will be in inches to the third, XI, also in inches to the third, and then we'll do some summations and we'll get our numbers. Okay, so our two components, we have a rectangle and we have a semicircle. We know that the area of a rectangle is base times height, which in this case is 30 times 50, or 1,500. Okay, the area of a semicircle. Well, we know that the area of a circle is 2 pi r. I don't know why that just escaped me for a second there. That's weird. Yeah, so, or it's pi, that's why, because that's a perimeter. I was like, what am I doing wrong here? So the area of a circle is pi r squared. So a semicircle is half pi r squared, or pi r squared over 2. Okay. So if I do that, I get pi times 15 over 2, which is, let's clear that, 3.1416, because I have a baby calculator, times 7.5. So that's about 20. Oh, that's got to be squared. I was going to say that's way too small. Pi r squared over 2. 15 times 15. There we go. Times 3.1416 divided by 2. All right, that's better. 353.4. I'm just going to call it 353. Okay. So I'm just rounding it a little bit. Okay, what's my y bar? Well, let's call this point my 0, 0. My y bar for the rectangle is half of the way up. Because of symmetry, this is 50, so my y bar here is 25 inches. My x bar, based on symmetry, is half of 30 or 15 inches. What about my semicircle? All right, if I go back to this formula page, I can see that here's a semicircle. This is can be confusing. This top line refers to the quarter circle. The bottom line refers to the semicircle. So it tells me that from wherever my cut edge is of that semicircle, that my centroid would be 4r over 3 pi from that edge. So in that case, that's going to be my x direction, isn't it? So my x bar of the circle is going to be 4r over 3 pi from the right, because that's where the cut is, right? My y bar is just going to be halfway up because of symmetry, so it's going to be 7.5 inches above 30. So 37.5 inches. Okay, so for this, 4r over 3 pi from the right, 4 times 15 divided by 3 pi, which is 45 divided by 9, more or less. 60, sorry, times 15 divided by 3, that's 20, and then divided again by pi. So hang on, 60, that's 20 divided by 3.1416. Yeah, so it's going to be about 6.4 inches from the right. So that means it's like right in here. Well, what does that mean in terms of my coordinates? It means that it's 30 minus 6.4 because I'm taking it back to here. Okay, so I take that number, subtract it from 30, and I get 23.6 inches. Right. Now we do yi times ai for the and then remember also the semicircle, this area is negative. All the coordinates, the x bars and the y bars, are all positive because they're all over to the right or up from my 0. But the area of the triangle of the semicircle is a negative. All right. So here, if I want to do y bar, yi, I would take 1500 times 25. And that number is 37,500. X bar I is 15 times 1500. So that number is 22,500. Now here, when I multiply the area, I'm going to be multiplying a negative times a positive. So in each case, these two numbers are both going to be negative because they're positive times a negative. So first we have 353 times 37.5. And that's a negative 13,237.5. And then X bar 23.6 times that area, which is a negative 353, is 8,330.8. All right. So now I need to sum up my areas. The summation of the individual areas is equal to the area. So that's going to be 1,500 plus a negative 353, 1147, and that's in inches squared. And then I find this Q sub X, which is 37,500 minus 13,237.5. So this Q sub X is a positive 24,262.5. And then my Q sub Y, which is the summation of these composite XI, AI, 22,500 plus a negative 8330.8. This number is 14,169.2. Okay, so that means therefore my Y bar is Q sub X over A, which is 24,262.5 divided by 1147. This is in inches to the third, inches squared. So my answer is going to be in inches. So I get 24,262.5 divided by 1147. And that is 21.153, 21.2 inches. And then my X bar is going to be Q sub Y over A. So that's going to be 14,169.2, same units, over 1147, same units. So my answer is 14,169.2 divided by 1147. And that number is 12.4 inches. All right, now let's go back to our diagram and see if that makes sense. If my X bar is 12.4, what that means is if it was just a rectangle, it would be at 15. It's a little bit this way because there's a big divot in it. So the stuff over here weights a little heavier than the negative space right here. And similarly for the Y bar, if this were 50 inches, I would expect it to be right in the middle. If it was just a rectangle, it's just going to scoot it down a little bit because once again, this weight is going to matter a little more because we have that cut out. All right. Do you have any questions about that? Not yet. Maybe?
Why is the white bar?
Yeah, because it's sort of by the definition. So back here, Q sub X is YIAI. So in other words, this is the summation of the Y bars. So the variables are reversed because if you're talking about a Y bar, you're referencing it from an axis. So it goes back to the idea of that being a moment. It's a centroid or a first moment. So it's still like a moment. So you have a distance and a force or an area in this case. However, you always have to reference a moment from a point or an axis. So that's what we're doing. We're orienting it to a direction. Q sub Y, on the other hand, is referenced from a Y directional axis because the perpendicular distance from the Y directional axis is an X distance. So there you go. So, yeah, so that's kind of the deal on this. So that's the first part of chapter 5. And I will be gone next Tuesday. I had an opportunity to go to the Idaho National Labs in Idaho Falls, and it's just a one-day deal. So I wanted to go see that. They do nuclear energy and nuclear energy research over there. So I don't know how much I'll get to see, but I'm pretty excited. But I know I'm pretty tickled. But aside from that, I'll be here for the rest of the week. I'll be here Monday morning and I'll be back Wednesday afternoon. So it's just a really quick trip. So if you need to visit about this, my plan is to be back in class next Wednesday, but also I'll be available in my office. So just choose Calendly if you need to talk to me, set an appointment and we'll get you squared away. Also, if you, we can get you registered if you're coming back in the fall. We can get you registered for classes if you just set an appointment with me. So, all right. Well, you guys have a wonderful day and I'm going to stop recording.